welcome to Improving Design with a Physically Based Render Workflow. I'm Teresa Nissen, and I'm the Director of Training and Professional Development for IALD. Before we start and introduce the speakers, I have a couple of housekeeping notes that you should be aware of. Please your cameras will be turned off and your microphones will be turned off for this session. Please put any comments about technical issues in chat, and if you have questions and answers for the speakers, please put them there as well. So this session has also been approved for continuing education, so that if you are interested, you qualify for one learning unit from the AIA, and you have to for the live webinar. The webinar may also qualify for continuing education credits from the CLD and LC, which are self-evaluated and self-reported. You can contact me at the address there, teresa@iald.org, for a certificate of completion if you need it. Now, I'd like to introduce our speakers. We have two gentlemen with us from HDR, and Trevor Hollins is the lighting design studio lead. He's a passionate advocate for the ability of great lighting design to transform spaces, and he holds a Master's of Architectural Engineering. From the conceptual stages of a project, he works closely with clients and the project design team to develop a lighting design that fully integrates lighting within architecture and improves the occupant experience. Jeff Thompson is a lighting designer at HDR as well, who focuses on lighting simulation and architectural visualization. Jeff actively works at integrating aspects of architecture, building systems, lighting, and photography to improve the communication of design intent and deliver a more realistic understanding of space. He has worked on implementing a variety of simulation techniques, including material scanning, virtual reality, and spherical high dynamic range imaging for site-specific virtual environments. So without further ado, let's watch the presentation. And again, if you have questions, please put them into the question and answer section listed below.
Yeah, so thank you for the introduction and welcome to Jeff and my presentation, Improving Design with a Physically Based Render Workflow. I'm going to change the slide. Yeah. We have integrated physically based rendering into kind of our design process over the past 4 years. And it's really been kind of an interesting journey for us. And so we kind of wanted to share with you today our journey and what we've learned and some of the mistakes we've made and some of the things we've done really well. These are the learning objectives. At the end of this course, participants will be able to do the following: identify the advancements in the field of graphics and visualization, determine the key elements in a physically based render image, outline the basic principles of a physically based render workflow, and apply cutting-edge technology methods to improve your design workflow. So this is kind of what brought us here: complexity. You know, everyone knows this, that with the the advent of LEDs, the way in which we're able to control light has become infinitely variable and infinitely controllable. We can control color, we can control intensity, distribution. Just kind of this. We have control of all the levers, and then at the same time, architecture. The complexity of architectural design has increased. Revit, Rhino, parametric modeling has allowed architects to create buildings and designs that are really would be impossible without the computer. And so those two things kind of came together to create a condition where it was becoming time consuming to perform calculations and work on design. So we're looking for kind of, what do we do? So we started to look at things, what do we mean? What's the value of simple models when they're being applied to complex structures? We think that the standard, of course, the standard process of sketches, coding diagrams, modeling, physical mock-ups, all these things can can be still used, to create successful lighting designs, and we're all here today because they do create successful lighting designs. But we think that maybe there's a better way that, we could use technology and we could harness technology to help, supplement the professional judgment that goes into these, designs with better information and try and take some of the guesswork out of the design process. So we started to look outside of the AE industry because we felt like we'd kind of reached, we pushed programs to their maximum. We looked at video games, we looked at movies, we looked at kind of the animation industry, and we realized they were dealing with some of the same problems. How do you make things behave realistically versus appear realistically? And so we saw that they were struggling with materials. Like this first image at the top, you have Big Hero 6. It's a fun movie, but there's a lot of lighting information happening in that image. You have different color temperatures interacting with materials. You have materials that are diffuse, materials that are specular. You have translucency of light passing through the main character. And so all these things are things that kind of add to the scene and kind of our understanding of light. And we saw movies with movies like Gravity, like obviously wasn't filmed in space but looks realistic. And how did they use sunlight to create brightness and shadow and the impact of millions of stars? How did all those things come together to create something that was realistic? And then lastly, Mandalorian. The Mandalorian, a big part of the Mandalorian is these alien environments, and these alien environments are part of the story, and they impact the characters, the Baby Yodas, and how does that all come together? Is that an important part of our design process? And is there something we can take from their production process and apply it to our design process? And so what we found was that all of these industries were using physically based rendering. And what that means is that an approach to computer graphics that seeks to render graphics in a way that more accurately models the flow of the real world. And so we asked two questions to ourselves. One, could physically based rendering be used by lighting designers to simulate the interaction of light in an unbiased manner with a diverse array of materials? And then two, with the goal being to achieve an accurate simulation of the physics based on the interaction of light with geometry and material. And I think kind of that unbiased, that simulation is important. We'll talk about that next. So we're always, I guess, two things. One, you're going to see a lot of pretty pictures today, and I think we're all used to seeing pretty pictures, and we call them renderings, and we know that, that's not how the project's going to end up. In the end, it's kind of a perfect approximation, and so we're not really here to talk about renders. We're here to talk about simulations. Can we actually physically simulate the interaction of light with materials to create, photorealistic, real representations of our designs? And two, renders, we like to think that they create bias. They impact the way we feel about design or a space before it's built. And everything we do creates bias that we as kind of lighting designers have to deal with, acknowledge, and then try and account for. Calculations create bias, coning diagrams, sketches, mock-ups, all these things are just approximations of the final built environment. And so, we think that maybe PBR, physically based rendering, may be a really good way to start to eliminate some of that bias. kind of example of the finished product. We found we really have been able to accurately simulate the interaction of light in an unbiased manner, and that's done a couple things. One, it's helped our design process, and two, it's actually kind of greatly sped up the design process, allowing us to iterate more and more on designs without kind of having to wait for calculations or mock things up. And I'll hand it over to Jeff.
Yeah, so Trevor's talking a lot about physically based rendering, but what exactly does that mean? And we think, there's kind of 5 components that make up the physically based rendering workflow. And, these are the 5 steps on the screen there: geometry, materials, lighting, context, and calculation. And what separates the physically based rendering engine from any other form of a rendering engine is that the materials and the lighting behave realistically. I know we've touched on that, and really, you see here the BRDF equation and the light transport equation, and we'll dig into those a little bit more as this presentation goes. So I guess what does that mean, though, is like Trevor said, we get really nice images, and we know that these nice-looking images are accurate because we're able to run calculations to back up our results, right? So we're able to know that lighting is accurate because we can run the calculation simultaneously and prove that it will look like that. And so we'll just jump right into the workflow here. The first step is geometry. The easiest thing for us as we're on the lighting design team at a full service AE, architectural engineering company. And so we work with architects on every project, and they get to use whatever modeling program they're interested in or prefer. And then we can take that geometry that they've modeled, whether it's in any number of various programs that you've heard of, Revit, Rhino, SketchUp, anything like that. And then we're able to export that geometry and import it into our preferred 3D modeling program, which is kind of like what the screenshot here that you're looking at is the modeling program that we prefer. And it's just a really simple export and import, and it really saves us a ton of time. We don't have to rework any of the geometry like you would in a radiosity-based modeling program. And it saves us so much time, and everything's way more accurate than traditionally. And so I'll hand it back to Trevor really quick here to kind of talk about this slide here.
Yeah, so we're discussing materials. Yeah, and this is a screenshot from The Lion King. And the amazing thing about The Lion King was that there was only one shot in the entire movie that was a real shot, and it wasn't this one. This is one of the fake ones, And so there's a lot going on here. On the one level, there's just a tremendous amount of geometric detail, but what really kind of turns this from art to real life is the interaction of light with the color and the texture of the materials that are there, and so we started to think, is there something we can do with materials to have them more accurately represented in our designs, and will that help our design process?
And so in terms of a physically based rendering engine, how do those materials become to behave more accurately? And the secret sauce is the BRDF equations or other related equations. So BRDF stands for bidirectional reflectance distribution function. And everything around you that you've ever seen has a BRDF equation associated with it. And it's just basically the physical laws of how light interacts with that material. And, the BRDF equation of a specific material can be measured in a lab or approximated mathematically. So that's how you kind of learn about the reflection, transmission, absorption, and scattering. And you can adjust these parameters in a material component in a physically based rendering engine interface. And that's what allows you to create these super realistically behaving materials. And so, you know, you see here on the right, it's a visual scripting interface that we use in our program that allows us to kind of control down to very small details in these materials and get them to behave accurately. And so what does that mean for us? Really, all it means is that we get really nice looking materials, again, because they behave realistically. And, you know, there's several ways that you can go about obtaining these materials. And, you know, you can, like I said, you can adjust these material component parameters basically on a mathematical scale or slider in the program to tweak it to get it to look the way you want. Or you can use third-party libraries or third-party companies will build material libraries that you're able to download and plug into your model. And then the third way that we know of is creating physically or photographically approximated materials that you can do that in varying levels of accuracy depending on your methodology that you use with the photography work. But that's a whole nother presentation on its own. And, you know, as lighting designers, we often work with radiosity-based lighting models. And in that case, you know, we're all typically used to what is called like the 80-50-20 model, right? So 80% reflectance ceilings, 50% reflectance on the walls, 20% on the floors, and that kind of gives us like, you know, that's kind of like been the standard for a long time on how do we approximate the materials in a space. But again, that involves bias. That brings bias into the scenario, and you know, what we're trying to do here is eliminate bias and render or calculate things more accurately. And so a lot of it goes back to how much time do I have? Like, do I really need these materials to look perfect? Can I just do an 80-50-20 model? And that may depend on what the use of this model that you're working on is. Is it going to the client or is it for internal validation? How many hours do I have to work on this project and all of that? So I guess before we talk about lighting, Trevor's going to talk a little bit about the inspiration for that.
Yeah, so Coco, another movie. You know, maybe not the most realistic looking, but at the same time, like I remember seeing this movie and kind of, you know, seeing kind of the city of the dead, and you know, really just kind of making my head hurt. You know, you're looking at, you know, millions of lights that are, you know, contributing to this scene to make, you know, a realistic space. You know, not that it's, you know, realistic, but you know, it's making it look believable. You know, and it's really, I think it's really amazing that they were able to do that with lighting. And then on the flip side of that, you know, you have daylit scenes, which is, you know, a single point source, but it's still interaction of light with, you know, materials, skin, you know, and how it creates, you know, light, shadow, and contrast, and how that's communicated to really help tell that story, you know. And so it's like these are super complicated things. Can we take what they're doing, and maybe not with millions of lights, but start to look at, you know, large numbers of lights, you know, holistically in our designs and see how that impacts things?
Yeah, so for normal audiences, this is the most complex and difficult part to explain. But luckily for this audience, because we're all members of the lighting design community, we should all be relatively familiar with IES files and using those to calculate our scenes. Again, there's a lot of complex physics happening. I touched on the light transport equation earlier, but the physically based render engine utilizes the physics happening with the light transport equation, which is how light propagates in the real world, the physical formula for that. And it takes your IES file distributions and intensities and accurately propagates that light source file within your model, and in that way we're able to run our lighting calculations. And so, you know, the interface we use for our 3D modeling program is super intuitive and user-friendly to place these light IES files within the scene. And I know in a lot of radiosity-based render or lighting models, it can be quite cumbersome to place these IES files and aim them accurately and get it to look the way you want. And you could spend, up to a week on a model that looks similar to the one on the screen right now, just placing those files and getting them to be oriented the way you want. But like I said, it's super intuitive for us, and there's helpful tools here. So
I think this is a really great image, because it really kind of does a good job of showing the complexity that's being able to be analyzed here. Just getting that geometry into a standard design program would it'd probably be impossible. And then placing those lights along curves, when you're changing in multiple axes, is super normally super complex, and is here is easy in a way that if we told you it wouldn't be, you wouldn't believe us, because it really you can array these things along splines, and it really allows us, once you have the materials in there, to really start looking at just fine details, and even kind of getting a start on final aiming, which is pretty amazing.
Right. Yeah, those are good points. And so I know if you're looking at the bottom of the screen, our kind of step-by-step process here, we're skipping 4 for now. Context is super important, but the calculations can be performed as soon as your geometry, materials, and lighting are placed. So we're going to jump to calculation, and then we'll jump back to context when time comes. But something to note when you're working with a physically based rendering engine is you need to be sure that your renderer engine is validated for accuracy by the CIE. And you can find the test cases and the documents produced by this organization to validate, or to see if your renderer is validated. And it's also important to note that a lot of physically based rendering engines, you can kind of tweak your settings to make it break the laws of physics. But so it's important to know what settings you need to have set correctly in order to make your renderer physically accurate. And so again, I know you've seen this a couple times already, but the BRDF equations and the light transport equations working together with your specific material samples and your specific IES files, that's what allows this calculation to happen. So there's a lot of complex physics, and I'd just like to reiterate that, because a lot of people make nice looking images and can run calculations, but that's what's making this specific case very possible. And so the program we use is an iterative renderer, so it'll continue to iterate, become more accurate, and more the visual acuity, more precise. Sorry. So the program that we use is it's an iterative renderer, and it'll continue to render until you tell it to stop. And with each iteration and each pass of calculations, it becomes more accurate and more precise. And so that's what you're seeing here with this video. This is sped up a little bit, but it's very fast, and it's becoming very fast because of recent advances in GPU technology. And when I say GPU, I mean graphics processing units. And so, like in the movie Coco that Trevor was referring to earlier, each of those frames that they rendered out to make that movie took hours and hours and hours, like hundreds of hours for each frame, because they were doing CPU-based stuff, which is computer processing units. But with advances in GPU technology, we're able to run calculations like this in just a fraction of the time, like literally 1/100th of the time in many cases.
Yeah. You can see the elapsed time down in the corner. You'll see, even though it's sped up, you're still only at 2 minutes right now. So, that's really, really quick. Yeah. And so the other thing that the program that we like to use allows us to do is to isolate variables. So, we're able to group lights together and turn them on and off. And I want to iterate or emphasize that this is all through one calculation path. Like, I click the render button one time, and then I'm able to manipulate these variables
by turning on and off groups of lights. Sometimes I can turn on and off geometry if I'm interested in that, and see the impact of these lights being grouped together and turned on and off, and see the immediate impact and effect on the geometry in the scene. So, we're showing this on a bridge, which isn't, necessarily super helpful, but, we use it for everything now. We're able to kind of input this shorthand code into the render window before we hit the render button, and then, we're able to turn on and off these groups of lights. So like in a conference room like this, we're able to kind of set our lighting scenes and kind of help fine-tune those lighting settings for the final project. And then, in this case, we're looking at a sky bridge at an airport terminal, and, we were interested to see, they wanted to do some color changing stuff, so we wanted to make sure that our colors and white lights weren't washing each other out, and we were getting the strongest effect possible from this. And we can also see the impact of the ambient lighting and how that starts to change your perception of the scene as well. And then in this case, we're even looking at restrooms, which maybe seems over the top. Restrooms aren't necessarily known for lighting design. But in this case, we were able to find that a distribution of a light fixture we were using in this restroom was causing some weird shadowing. And so we were able to isolate those variables to see that shadowing occurring. And then we were able to use a different IES file, a different light source distribution, and help mitigate that issue. So we think it's super helpful for, basically anything, but especially it's incredibly helpful for some members of our lighting team here in Omaha. We were able to, we were working on a hospital project, and some of the doctors at the hospital were concerned when they saw this colored head wall in this neonatal intensive care unit room. And they were worried that the coloration of the head wall would cause ambient lighting to cause coloration in the skin of these babies, and then that would, alter the way that they were evaluating their health condition. And so we were actually able to isolate the indirect interactions between the head wall and the patient bed, and determine that there was such a low percentage of light being contributed after that secondary bounce, after the initial bounce on the secondary path from the head wall to the bed, that there would be little to no skin coloration issues to cause concern. So we thought that was really special, and now I'm going to turn it back over to Trevor really quick to talk about jumping backwards from 5 to 4. We're going to talk about context now.
Yeah, so, I guess, what we've kind of seen is, a brief overview of our process and what kind of, our evolution over the past 4 years, what that's looked like, and how that's, kind of changed the way we work. It's been really, it's been an amazing process. We really think it helps us, understand how the lighting design goes together, the different layers of light. It helps us communicate the importance of, kind of the layers of light that are making up a scene to owners. Because if they're like, we don't want to pay for kind of this accent stuff, we can just turn it off and show them, what impact that's going to have on the project. And so it's been amazing. But, so what do we do next? And so we started to think about context. Our designs, the buildings we light, they don't exist in a vacuum. And they, the local surrounding community has an impact on that design, and these designs impact the community. And so is there value in looking at that? Can we look at that? And so we I know, like Star Wars. We were watching the Mandalorian, and we found out that the Mandalorian lit their scenes with giant LED kind of walls and ceilings, and they used those walls and ceilings to project the environment onto the actors. And so what that did is it the reflections of the environment in the armor, on, on the characters, on the aliens, really placed those things within, kind of these alien environments, made them realistic and, I don't know, and part of one kind of whole cohesive movie scene, and so, we I don't know, we've done a lot of talking and we're like, does that apply to us? Could we do this, and would this have value to our lighting design? So that's kind of some of the stuff we're kicking around right now. And so here's kind of some R&D, look at some R&D stuff.
Yeah, so we're kind of departing from like the regular lighting design tasks and into more of like the whole design as a whole discipline, and how do we improve that using this physically based rendering workflow. And so, like Trevor just touched on, context and your immediate surrounding and your ambient surrounding environment really play a huge role in how you perceive the geometry and the materials and the lighting. And so, I think everyone's familiar with Frank Lloyd Wright. His house, Falling Water, is one of the most famous. Yep, one of the most famous pieces of architecture probably ever, at least in the United States. But as you can see here, if you take it out of context and you take away some of the material and some of the environmental lighting that's occurring and interacting with it, it really becomes just like a completely different project. And so Trevor likes to say, like, would you design the building on the left the same as you would the building on the right? And the answer is yes, and the reason is context. And so, I talk a little bit about immediate surrounding context and ambient surrounding context, and how do we first things first, how do we take care of the immediate surrounding context? And one of the things that's really challenging for lighting designers, especially like with landscape lighting design or roadway lighting design, is vegetation and trees and bushes and things like that. And I think, we can all use our professional design judgment to make the right call a lot of times, but if we can simulate each and every leaf and each and every branch on each and every tree, you kind of take your guessing work out of it. And, so with the 3D modeling program that we like to use, there's plugins that allow us to kind of create these really hyper-realistic vegetation models. And that allows us to evaluate our lighting design in context with the real vegetation in the scene. And so we thought that that's worth sharing. And then, as Trevor alluded to with the Mandalorian methods, I guess, is the way you can do this they did it with giant LED screens and just projecting intense light from those screens at different colors. But the way that we were able to do this in our 3D modeling program is by shooting high dynamic range images. And so basically a high dynamic range image is you take your digital camera and you shoot several different exposure value brackets to capture the full luminance range of the scene. And so that's how you take one high dynamic range image. And then if you want to take a 360-degree spherical high dynamic range image or photosphere environment, you do that at all the angles around basically your tripod stand. And then you have to merge those photos together and stitch them together to create your 360-degree spherical environment. And then if your program has image-based lighting capabilities, luminous data retained in that high dynamic range spherical image will contribute accurately in terms of intensity and direction, if calibrated properly, to the model placed within the scene of that environment. So that's kind of what this diagram is showing here. You see kind of like your unlit condition, but on the right, you start to see, how does the light really interact just in terms of ambient contribution to that model. And so that's what we started to look into, like how do our designs fit into a real world scenario. So this is just the first test I ran with a 360 spherical high dynamic range environment. And this is actually just our office building. It's just on the floor we work on in a waiting area. And it's stretched out to show you the whole image, but it's a spherical environment. And, this is an image from, we were helping some architects evaluate glazing samples. So this is a glazing unit here with a piece of vision glass with a little bit of a spandrel at the top next to a full-size spandrel, and we're calling that just the individual glazing unit. And so, the thing that I think a lot of architects or designers struggle with is how do we account for the color shift between through layers of glass onto different colored materials, and how does that really affect the overall end product? And if you're spending millions of dollars on a giant glass building and you're spending all that money on glazing material, you want to make sure you get it right, and you want to make sure it looks the way you're telling the owner it's going to look. And so we've got, this is just a real quick video. It's kind of a demo I put together to show how the light from the 360-degree spherical environment of the high dynamic range imaging is contributing to this singular glazing module that we're evaluating here. And then, so that's me moving around it, and then we're also able to adjust the exposure values and see how that looks. So it's behaving as the real world does. If you take your phone out and you try to take a picture next to some windows, it often gets blown out because the exposure value needs to be adjusted. And so it's behaving as though it's a real world scene. And again, the point of this is because, glass is complicated for this particular scenario, but the point is that, your surrounding environment really impacts the way you perceive the geometry and material that you're evaluating. And so this is the same glazing unit with different surrounding environments. And you can see how drastically different it looks just because it's indoor and then bright in the outdoors and then at a sunset condition and then in an urban environment with some warm lighting nearby. And it really has a drastic impact. And, if being able to evaluate one material in several different environments can maybe help you make a smarter decision on material choice. And so, that was kind of this quick case study we're kind of running through, and then we finally put it all together, kind of built this facade, stuck it in a high dynamic range spherical environment, and we were starting to see okay, we need to make some adjustments on the material color of that top spandrel. Maybe, we wanted to adjust the spandrel colors, maybe we're adjusting the glass types. And then, this is another demo video I put together of me adjusting the sky condition from the high dynamic range imaging and then making material adjustments on those spandrel colors to kind of help the architects make decisions. And so I think, I feel like I've been rambling a little bit, but I think we see some real potential value, and we think that the people we are working with see the potential value here. And, we're starting to really help shape design because we have a unique insight to the built condition in real world environments. So, and then as lighting designers, we like lights at night, typically, not necessarily just during the day. So, this is kind of how having those accurate materials that look correct during the day, how does that transition to the nighttime environment, and how do we pick out, the spots that we're the most interested in for lighting. And I don't know, Trevor, do you have anything you want to say about this?
Yeah, I think it's putting it all together, understanding, how our design impacts architecture and how the environment impacts, our design and architecture, and how that all kind of coexists is really, it's an interesting concept. And, we've always been able to, approximate things or, use our experience we've gained to understand how we think it's going to happen. But now we can really validate those interactions and validate kind of the final product before things are built, without the use of mock-ups. Mock-ups are super important. but not every project has the budget for mock-ups, and even a mock-up is just a section, so you don't get to see the impact over, a large area. And so, maybe it all comes back a little bit to bias, and, what can we do to eliminate bias, to give us, kind of better information to make more informed decisions on. And we think physically based rendering has helped us do that, and we think it, really has a place within kind of the lighting design profession. So, I guess thank you everybody for joining us today, and we're ready for some questions.
Yeah, thank you.
Well, great. Thank you, gentlemen. We have a lot of questions that have been posed, and I will address them to one or the other of you. And for all of you attendees, just so that you know, they have graciously agreed to answer your questions, even though we won't get to all of them probably in the session. If we don't, they will answer them, and then we'll post them along with the video, so that you should hopefully get your questions all answered. But the first question, and one that has been repeated many times, is what is the modeling program that you are using in your demonstrations?
Yeah, so can you hear me first?
Yes.
Awesome. Sorry about the audio quality. We use 3ds Max with a rendering plugin called IALD, and we found it's the easiest to work with. There are a number of other kind of modeling programs that we think you could probably do this in. Maya, Unreal seems like it could be really promising, but we haven't found kind of a render plugin that's as easy to use as we feel IALD is for what we do. I guess, do you want to add anything to that, Jeff?
Nope, that's it. Yeah, we use it every day and we love it. So.
I guess that leads to another question then about, do you have team members who are committed to only running these calculations as specialists? Or is the calculation approach user-friendly enough that all design members are capable of running calcs with this program themselves?
Yeah, so, there is there's a little bit of a barrier entry there on difficulty, but, really the placing of the light fixtures and the running of the calculations is, no more complicated than it would be with AGI or I don't know, visual, or kind of any of those kind of more typical programs. There are, because you're working within 3ds Max, there's a lot of buttons, and there's a lot of things that kind of look intimidating, but we're really only, because we're only using it for lighting calculations, we only use a small portion of that program to do the work.
Okay. Let's see what was. So if it says if you're using BIM workflow, do these lights exist within your BIM model, or do you have to rebuild the lights in BIM in your rendering program?
You want to take this one, Jeff?
Yeah. Yeah, so you can, I know a lot of probably companies and people here are familiar with Illum tools, or you're able to link an IES file to a BIM luminaire object, like in Revit or something. You can do that. And if you were to export, a chunk of a model out of Revit with a luminaire with the IES file linked to that object, it would transfer to into 3ds Max, which is what we're using. Although the IES file may not link properly and the path may not stay live. So you'll may have to do some relinking work. For us, it's probably usually just easiest because we're kind of like doing the lighting for the first time in the 3ds model as opposed to in Revit, that we won't worry about IAS files in the BIM model or the Revit model, and we'll just work on it kind of in a standalone 3ds model, and then kind of place the lights using the BIM software like Revit later on once we've kind of tightened up our design a little bit. At least that's kind of how I work more often than not. Trevor, I believe you're the same, but feel free to explain the other ways if there are any.
Yeah, it's, your Revit model is kind of always constantly changing thing. Walls are always moving, doors are always being added, and so we've kind of found it easier to work from a point in time and not have to worry about kind of that constant churn. So we kind of place the lights within 3ds, run the calculations, and then kind of move that documentation over into Revit.
Okay. Let's see. I don't see the physical geometry of the lights in the model you are showing. Is that intentional?
Yeah, so depending on the use case, we'll show the physical geometry of the light. Like if it's something we're concerned about, it being visible to occupants of a space that we're designing, we'll show it, or we can model it, or we can use, the BIM models that are available on most manufacturer websites. We can bring that into our model. In a lot of cases, though, like with recessed lighting or something that's in a wall, or the actual fixture housing itself is not visible, and so in that case, we really just end up showing the lens or the light, the light shape of the actual aperture. In which case, we just use kind of the 3ds Max lights to show that. Does that make sense?
Yeah, I mean, I think it's I guess it's hard to kind of grasp this because you're used to seeing things that look really nice being renderings, and those renderings being kind of really large hits to project budgets and time spent. But this, with what we're doing, this is really, we've found that it's faster to run calculations in this manner than it is to run calculations kind of in the traditional radiosity pipeline. And so a lot of the images that we're showing are just kind of like our internal proof of concept images. And so we may just be looking at them inside of the office, or talking to architects about that quickly. And so we haven't taken the time to go in and put in kind of the physical luminaire housings. And so if we're taking it to a meeting, or there's kind of a higher level of analysis needs to happen, we'll take the time to do that. But it's pretty amazing to kind of think that what you're seeing is really just our day-to-day down and dirty kind of work process.
And I think that kind of leads into the next question, which is, does 3ds Max handle very large and complex model? How long does it take to run one of those calculations?
Yeah, so 3ds Max definitely can handle really large models. I think a lot of it is actually, I kind of touched on it in the presentation a little bit, but it's more based on your graphics processing units, which is just one component of a regular computer, right? So if you don't know much about it, we didn't either when we first started, and kind of become obsessed with it because it starts to matter a lot when you're doing this type of work. But I think, yeah, it's not so much the software that struggles with like large complex models as much as it is your hardware. that struggles with large complex models. So it's you spend more time and resources on getting the right hardware to do the job correctly. And when you have the right hardware, it's lightning fast. It takes almost no time at all to get really accurate calculations and really beautiful visualizations. I think, Trevor, do you have anything to add?
Yeah, I mean, 2 to 10 minutes is kind of your standard calculation run for something, and then using light path expressions, which Jeff talked on, you can kind of segregate different groups of lights, so you can look at, indirect, accent, direct, general illumination. You can kind of break, kind of all your layers of light out. You can run one calculation and then be able to look at, kind of the visual effects and also, the calculation levels associated with each of those levels, and even, combinations of those levels with one, calculation run. So it's I don't know, it's a complete game changer, because, if you get a project of any kind of size with, kind of traditional calculation software, really, you can be 30 minutes, an hour, on a calculation on the low end.
Okay. Actually, to follow up for that question, that for the time that you said that 2 to 10 minutes to run sounds like a really short time for a complex model. What hardware do you have that can do that? Or the complex models much longer than that, which is what I think.
Yeah, no, that's a complex model. And, we've kind of evolved at the same time as kind of movies and computer games and all this stuff. And so there's really been this doubling of performance, and like what you could do for a large amount of money 4 years ago, you can now do for not a lot of money at all, and really kind of reasonable spec computer. There's been some graphics card releases in the last month that we were looking at kind of upgrading our system, and we found that like kind of the new graphics cards that have come out. I don't know how much cheaper was it? It was 4 times cheaper for.
Yeah, they're 4 times cheaper for 4 times the performance of the last generation of cards. So there's literally nothing else in the world that progresses like that. So it's an exciting time to be interested in this kind of stuff.
It's not a monster machine. If you have kind of like a standard higher end consumer grade graphics card, you're probably set up pretty good for one person to run those calculations.
Great. And then I have one that says, as an EP who wants to dive into PBR at home, what sort of GPU would you recommend for a PC? Any suggestions?
Yeah, so I mean, getting into, I guess, an actual product. So like the iRays run off of, you need an NVIDIA based GPU to use iRay, which is what we use. And we're super excited about the 3080 that just came out, because it's got a fair amount of RAM in the GPU, and RAM's kind of your limiting factor on how big of a project you can run. So the more RAM you can get in your GPU, the kind of the bigger projects you're going to be running.
But it's not really like one card is the right answer. it kind of depends on like what your budget is and how many cards can you afford? You know, what types of models are you really looking at? Kind of what are your expectations, and like how often are you going to upgrade your hardware? Like that sort of a thing. There's no one right answer, and I think Trevor and I could put together like a year's worth of presentations about hardware and software trial and error and things like that, just from all the stuff we've learned over the last few years. So there's not really one answer, but like if people have specific questions, maybe they can reach out to us and we can kind of like work with you one-on-one or something on that.
From a price and performance standpoint, we're kind of like, that would be like the floor entry point.
Yeah.
Great. Well, if whoever asked that question wants to reach out to IALD, we can then forward the question on to Trevor and Jeff. Then also there's a number of them about IES, and that are you modifying the IES files once imported to the render calculation program? We've done this in the past and found that the IES files did not provide accurate results, specifically with the 3ds Max. And then how do you get around the fact that IES files still treat everything as a point source?
Yeah. So I think that there's a known bug within 3ds Max where it imports everything in candelas instead of lumens, and sometimes the way IS files are set up, it does that. It makes that conversion incorrectly. So if you're checking your IES files and making sure that the kind of the imported lumens, the lumens that it's stating around, kind of that the luminaire has when you import it, match what they should have based on what you're specifying, we found that it's accurate.
I'd say it's also important. Yeah, it's also important that so calibrating your IES files with the proper lumens, like Trevor just said, and then also using the right light shape. A lot of times there's different light shape categories you can choose from in 3ds Max, and we found some of them work better than others. Some of them are less accurate than others. Some of them redistribute the IES files distribution incorrectly, depending on placement and orientation. And you know, I think those are known bugs, at least known to us through trial and error, and probably can be confirmed by other people in this presentation that have looked into this before. I'm sure you've found something similar. So yeah, it has its limitations, and there are bugs, and 3ds is a finicky program when you're working with complex models, but just kind of have to pursue through that or persevere through that, I guess, and do what you know.
You have to use discs or planes.
Yeah.
Kind of flat shapes. If you bring it as a point source, you bring it as a sphere, it won't calculate correctly, because if you think about it, that's kind of how IES files define things, as discs or rectangles. So you have to go at it that way. Yeah.
Looks like somebody got a 3080. You guys are lucky.
So do you identify this as a separate scope of work, or is it included in your basic services?
Yeah, I mean, it's replaced kind of our standard calculation, our standard calculation process. What we have found is that, we start bringing these images to meetings, and then people start asking us what else we can do, and they start asking for, more renderings and to see more images. And so, that kind of we found that it's led to more work or additional work. But you definitely have to be careful not to, kind of become the the visualization part of the team without that scope being clearly defined.
Okay, well, thank you, gentlemen. This was, we're out of time. We still have a number of questions left, but I will send them to you. And then if you can get me the answers, we'll post them after the conference is over so that the attendees do have all the responses they're looking for, because I can't talk to you in the hallway and over the coffee break. But thank you again. Thank you so much. And I think the next session we have is the ILD update. So hope to see you all there.